Okay, thank you. So the past 3 lectures were all about data structures, partition trees, cutting trees, and so on. Today and, well, tomorrow, although tomorrow I also do a little bit of data structures again, but today is all about arrangements and combinatorial problems, bounding the complexity of arrangements or certain substructures in arrangements. So I guess it's similar to these data structures in the sense that for many, many problems in computational geometry, somehow if you start working on them, then arrangements start to play a role. And to analyze the time complexity of your algorithms, or maybe the complexity of the structure that you're computing, often the complexity of arrangements, but especially certain substructures in arrangements play a very important role. So again, this is something where you need, well, at least you need to know the type of results that exist. Of course, there's lots and lots of results in this area, and well, I don't know the details of all of them, so that's not really that important. But what you should know is the kind of things that exist, so that if you need something, you realize, this is probably known. Let's look it up, and then hopefully you can use it. So today I want to talk about arrangements. I'm going to mainly talk about it in 2D. So similar to the partition trees, I'm going to explain everything in 2D. Actually, for most of the problems, there's also results in high dimensions. Although unlike partition trees, so for partition trees, if you know how to do it in 2D, you also know how to do it in higher dimensions. Here, you can sort of guess the bounds that you get in higher dimensions, but the techniques to obtain them between 2D and higher dimensions are quite different, and high-dimensional proofs are a lot more difficult. Okay, so what's an arrangement? Well, you can define an arrangement on any set of objects. Often you look at lines, but it could also be segments or curves or disks or anything. And then if you look at these objects, so it's usually easiest to think about only the boundary of the object. So if it's a segment, it's just a segment. But if you look at an arrangement of disks, maybe you would actually take an arrangement only of the circles that are bounding the disks. Okay. Then these objects will partition the plane into different regions. Okay. So you get, in 2D, you get a planar subdivision. And, well, the arrangement is this subdivision. So it has vertices, which could either be like here, if you have segments, an endpoint of one of the segments, or it could be an intersection point. You have edges, which are parts of your segments or your curves between two of your vertices, and you have faces. Okay? How many faces do you have in this arrangement? 3, right? Because it's 1, 2, but also this unbounded face. Okay, and, well, the combinatorial complexity of the arrangement is simply the total number of faces, edges, and vertices. Okay, and what we're going to do today is look at what to prove bounds on the maximum complexity of, I don't know, maybe the whole arrangement, or maybe just a single face in the arrangement, or things like this. Okay, so in particular, we're going to look at, first of all, the whole arrangement, but that's actually pretty easy. Then I'm first going to talk about what is called the upper envelope. So if you have, let's say, segments, and you look at the segments from above, then the upper envelope will be what you see. A different way of defining it would be to say, okay, each segment or maybe a curve, well, you can actually say I have a function defined from here to here, where the value of the function is simply the height of the segment, and now the upper envelope you get if you take the maximum of these functions, right? So here, this is the highest, here this is the highest, and so on. Okay, so we'll first look at that, then look at the complexity of a single cell, single phase. We're going to look at the complexity of, well, a number of cells, but the cells that are given by, well, take all of the ones that are intersected by a line. Look at that very briefly. And then we're going to look at the K level, or, well, actually the at most K level. So the K level is, well, like here, this is on the 1 level, because every point here you have exactly one line below you. So here, this line is below, here, this line is below, here. Well, actually this line continue, so that line is below. Okay, so these are the things we're going to look at. But let's first do some trivial things. So if I have an arrangement of curves in the plane, okay, any two curves can intersect at most s times, so s is a parameter. So here s would be 2. Okay, what is the total number, well, what's the complexity of the arrangement? And, well, it's pretty easy. So what's the number of vertices at most? Well, Sn squared. Or maybe if we're a little bit more precise, we would say, well, for every curve I have 2 endpoints, so that's 2n. And then for each of the n choose 2 pairs of curves, I could have s intersections. So in the worst case order, s times n squared. So that's easy. What's the number of edges? Well, that's also pretty easy. You can say, well, take one of my curves. Okay, there could be a lot of edges on that curve. How many? Well, it's going to be somebody still. Well, okay, so I have a curve, I have a number of intersection points, and then the number of edges is the number of intersection points plus 1. Okay, how many intersection points? Well, in the worst case, every other curve could intersect this one in s points. So I get s times n minus 1 plus 1. And, well, I can do this for n curves, so that's it. Okay. Number of faces, what do you use? Euler's formula. Right, so you use this, and then you use these other bounds, and that's it. Okay, so this is very easy. So let's look at something which is actually a lot more challenging. So let's look at this upper envelope. Okay, so the general question would be in 2D, I have curves, and let's say for now, or what people usually say is they're x monotone. Okay, so that means that you can indeed view them as, well, the graph of a function. Okay, partially defined function. And again, any two such things intersect at most s times. Then what is the complexity of, well, this envelope, so the maximum of all these functions? By the way, suppose they're not x monotone, what would you do? I say, okay, I give you s curves that are maybe polynomials of some small degree, but the polynomial, it could be something like, I don't know, it could also be this. Well, if it's a polynomial small degree, then it will have only a constant number a small number of places of vertical tangency. So you simply cut the curve into a number of pieces. Right? Then you get a number of pieces and then you apply it to those pieces. And of course the number of pairwise intersections, it can only go down now. I mean, you intersect a piece fewer times than you intersect the whole curve. So this is not really a problem that we're only looking at X monotone curves. Okay. By the way, who already knows what the bound is? Nobody? Okay, so that's good. So at least you'll learn something today, hopefully. Okay, so this is actually not very easy, but let's first look at something where the question is easy. Namely, if I have just my curves are full lines. Okay, so what's the complexity? N. Right? So the number of edges actually is at most exactly n. So why is that? Each line can contribute at most one edge. Okay? So that's very easy. What happens if I give you curves where S equals 1? So every two curves can intersect only once. Yeah, it's exactly the same thing, right? Because the argument is that, let's say, look at this curve. I follow the curve. At some point, it starts to define an edge. Okay. Now it ends. But then it ends because it intersects something else. And then because I have only one intersection point, it can never go above this one again. So it's after it contributes an edge, then it's completely gone from the upper envelope. So this is very easy. Now look at something that's maybe the next step. So instead of full lines, I have line segments. Okay. And now it actually becomes quite difficult. So, what would you guess? Or maybe somebody has seen this bound. So it seems if you start playing around with examples that, I don't know, maybe it's not just n, but, I don't know, 2n, 3n, or... but actually... it can be a little bit more, but we'll see. So the tool that we need to prove this is our so-called Davenport-Schinsel sequences. So what's a Davenport-Schinsel sequence? It's just a sequence of elements, numbers if you want, and this sequence should have a few properties, two properties. So I have a Davenport-Schinsel sequence of order S on n symbols. Okay, so let me simply say the symbols are 1, 2, 3 up to n. Okay, so you just have a sequence 1, 3, 5, 2, 2, 5, and so on. But there are two conditions. One is that you're never allowed to put the same symbol twice in a row. Okay, so 1, 2, 3, 5, 5 is not allowed, because you should first have something else in between before you can use 5 again. Okay, so this is the first thing. The second thing depends on this parameter S. Okay, and it says that, for instance, if S equals 1, then you're not allowed to, well, you use some symbol I, and then later you've used some J, then you're not allowed to have another I. Okay, so the sequence, the subsequence iji is not allowed. And there can be other things in between. So this is not a consecutive subsequence, but just different things. Okay, so when s equals 2, it's not allowed to have I, something else, j, I, j. Okay? In general, if I have, for arbitrary s, you're not allowed to have such a sequence of length s plus 2. Okay, so for s equals 3, it's not allowed to have I, j, and so on. Okay, so look at this sequence. Okay, it's a Def-Bort-Schinsel sequence using 5 symbols. And it's a Def-Bort-Schinsel sequence of, well, what is the order? Okay, so indeed, I never have 2 times the same number in a row. So the first condition is indeed good. So it's a Def-Bort-Schinsel sequence. And yeah, so I have this, here I have 1, 2, 1, 2. Okay, so, and that's, I also have 2, 3, 2, 3, but I never have something where you have 5 in a row. So, actually, this should be 3, right? Because I do have this 1, 2, 1, so I have it for 4, but not for 5, so this should be 3.
What's the 5 sequence? It's 2 is correct. There is, you said there is a 5 the subsequence in length of 5? So
No.
Must be 3.
So, what I'm saying is that the longest alternating sequence, right, has the longest alternating sequence has 4 symbols, right? So I don't have something where I have 1, 3, 1, 3, 1 or something like that. So the longest is 4, okay? So, but for s equals 2, 4 is not allowed. So this is a Def-Bort-Schinsel sequence of order 3. It's also a Def-Bort-Schinsel sequence of order 4 or order 5, but 3 is the smallest number here. Okay, so is the definition clear?
It's 4 segments.
No, we're just talking about numbers now.
Upper envelope of segments.
We're going to use this later, but don't think about segments at the moment. This is just about sequences of numbers. Okay? So, well, later we'll see how you can use this for upper envelopes, but for now just think about I have a sequence of numbers. This sequence has certain properties, and the question is how long can this sequence be? Okay? So, the notation that is typically used is lambda s of n. That's the maximum possible length of such a sequence. Okay, so that's going to be a function of n and s, right? So for different values of s, you can, of course, the higher s, probably the longer you can make the sequence because you're allowed more longer alternations. So for s equals 1, I guess I have these two, then I'm not allowed to repeat the same symbol twice in a row, and this is not allowed. So I guess if you think about it, it's very easy to see that the sequence cannot be longer than n. Right? Do you see it? Because what happens is, well, I can use a symbol, let's say the first 1, 2, 3, but but I'm never allowed to use the same symbol again, because as soon as I use the same symbol again, well, I'm not allowed to use it immediately after this one, because then I violate this. And if I put something else in between, then I immediately have this. So you can never repeat a symbol more than once. So obviously it can have length at most n.
For the case where s equals 1, can't we have 1, 2, 3, 4, 1, 2, 3, 4, for example?
Okay, so the question is, can I have 1, 2, 3, 4, 1, 2, 3, 4? No, because I have 1, 4, 1. Actually, even another 4, but this is already not allowed. Right, so this alternating subsequence, I, J, I, this could also be empty. Right, that's okay, so so now I want to prove that when s equals 2, now I can make it a little bit longer, right? Because, well, this, for instance, is allowed. But it cannot be very long. So this proof is, fairly easy. Probably if I would give you like 5 minutes or something, a number of you would come up with it. So the proof is the following. So look at, let me simply number the symbols in the order in which they appear. So the first one is 1, then 2, and then, well, maybe I have 1 again, but as soon as I have a new symbol, I call it 3, and then if I have another new symbol, I name it 4. And now look at the last symbol, right? So the symbol where the first time it occurs, that's last. Okay, so my symbol n. So here is my symbol n. So I have lots of things before, but in here I haven't used n. This is the first time I use n. Okay, so I claim that I can never use n again. Okay, why is that? Yeah. There should be j. Yes. Yeah. I can never use n again because, well, after this one I'm not allowed to put it here. So I have to put something else. But then, since this was the one that the first occurrence is last, I know that the 6 was also here somewhere. Okay, so I have the 6 somewhere here. Then I have n, then I have another 6, and since ij is not allowed, well, I cannot put my n. So this n occurs only once. Okay, so now how would you continue the proof? Well, the idea would be to somehow maybe this n doesn't happen again, so you remove it and then you have a Dev-Bojinzel sequence perhaps with only n minus 1 symbols, and you apply induction or something. Okay, so let's see. So it's something like, okay, I remove this one. Okay, so what is the length that I can get here? So the length of a Dev-Bojinzel sequence of order 2 with n symbols. Well, if I remove this, I would have plus 1 here maybe. So is that correct? If I remove this, do I get a differential sequence with n minus 1 symbols.
No, maybe not. Maybe there is two equals two same symbols, and it is between those two.
Yes, very good. So indeed, if I remove this one, then the new sequence is still going to satisfy this condition, but it may violate this condition. If I have a 6 here and a 6 here, and I remove this one, then I'm violating the first condition, so I don't get a Dev-Bochinzel sequence. So what do?
Can remove 12.
Yeah, so if these are different, I remove only this one. If they are the same, I remove this one and this one. Okay, and then, of course, I cannot have a problem that these two are now the same, right? Because I remove this one only if it's the same as this one, and these two are not allowed to be the same. So I get this, right, where maybe I have to remove another one. And, well, the maximum length, if I have only one symbol, well, is 1. So you get, at most, 2n minus 1. So anybody has an idea whether you can actually get 2n minus 1? So can you make a sequence which is that long, or perhaps it's smaller?
Yes, it's possible.
How?
1, 2, 3, 4, 5.
Yeah.
Repeat it again because twice. 1, 2, 3, 4.
Okay, up to n, and then you're saying 1, 2, 3, up to n minus 1? Is this allowed? Because now I have 1, 2, 1, 2. Yep. So here I do, well, let's just do 5 and then 4, 3, 2, 1. Yeah. Right, so also if you think about it, it corresponds indeed to the proof, because what happens is that every step of my proof, so to speak, I am really, now these two are the same, so I have to remove 2 symbols. And then here, this is the one, I remove it, but these are the same, so I have to remove another one. So this bound is tight in the worst case. Okay, so for s equals 3 and higher s, the proof is extremely complicated. So I'm not going to give it. The bound is, for lambda 3, is n alpha n. You have all seen alpha n before, I guess, if you look at union find with path compression. So alpha n is a function that grows very slowly. So it's smaller than log n. It's smaller than square root of log n. It's smaller than log n. It's smaller than, you have this log star n, which is how many times you have to take the log before. It's smaller than, well, basically everything. So I think if you take like the number of atoms in the universe, then alpha n is 5 or something. So it grows very slowly, but it's still growing. And so you're not allowed to say that this is O of n, because it grows slightly faster, but in practice it's really, really very small. And actually, for any constant s, this is almost linear. Right, so the next term is lambda 4 is n times, so the lambda 4 of n is O of n times 2 to the alpha n, which is still, this looks that it grows very quickly because this is in the exponent, but still this is smaller than log n, than log star n, because this is growing so slowly, even this exponential thing is growing very slowly. So this is, for every constant s, all of this, for instance, is smaller than n log n. Okay. So now let's see how we can use this for upper envelopes. So it's actually not so hard. Okay, so let's say I have n functions that are, or curves that are infinite. Right, so they go from x minus infinity all the way to x plus infinity. So they're fully defined functions, x monotone. And now I claim that the complexity of the upper envelope is order lambda s of n, where s is the number of intersection points. Okay, so how would the proof go? Well, I write here which function appears on the envelope. And now I want to argue that this sequence of numbers is a Davenport-Schinsel sequence. Okay? And in particular, I argue that this is a Davenport-Schinsel sequence with n symbols, okay, n functions, so obviously n symbols, of order s. Okay? So, let's see, why is it a Davenport-Schinsel sequence of order s? Well, if you have something where here I've function I, then here j, and then here I, whenever I have I here and j here, in between these two must intersect. Right? Because here this one is higher. So if you have an alternating sequence of length t, then I have t minus 1 intersections. Okay? So if you allow s intersections, well, then you can have an alternating sequence of length s plus 1, but s plus 2 is not possible, because then I would have s plus 1 intersections, which is not allowed. Okay, so s plus 2, you don't have an alternating sequence of length s plus 2, so it's a Davenport-Schinsel sequence of order s. Okay. Okay, so now let's make it a little bit more difficult. So instead of infinite functions, I'm now going to take partially defined functions. Okay, like here. So we're going to do the same thing, right? We're going to write here all the functions that appear. Maybe I should also, because there could be places where none of the functions is defined. Right, that's like here. So, well, maybe you need to add an extra term n or something for that, but let's ignore this. Okay, now actually it's a little bit different, because as you can see here, even though I have only one intersection, I can still have ij, because the argument used to be, well, if I have I here and j here, then here j is above I, and here I is above j, so I must have an intersection. But now it can happen that this one simply ends here. So there's no intersection here. Okay? So that can happen for the leftmost one and for the rightmost one, but in between you must always have these intersections. Okay, so now instead of getting t minus 1, you get t minus 3 intersections, because you have these two at the end points, you get two more things. Okay, so that means that, if you would, so that the order of the Davenport-Schinsel sequence is no longer S, but S plus 2. Okay, you cannot have S plus an alternating sequence of length S plus 4, because S plus 4 would imply S plus 1 intersections, which is not allowed. If you're not allowed to have an alternating sequence with S plus 4 symbols, then you have the order of the Davenport-Schinsel sequence is S plus 2. Okay. Let's see. So this is the theorem. Okay. So if you have fully defined functions, then the upper envelope was lambda s, right? And note that when you have lines, well, we already knew that for lines it was n. But for lines intersect at most once. So then you plug in S equals 1, and we also saw that the maximum length of a Davenport-Schinsel sequence is of order 1 is linear, so that's fine. Actually, for fully defined surfaces in 3D, for instance, you would get n squared, or actually the best bounds that have been proven are n squared plus epsilon. So basically, when you look at the envelope and you compare the complexity of the envelope to the complexity of the full arrangement, you typically lose one factor of n. Okay, so the full arrangement in d dimensions has complexity n to the power d. Okay, so for instance, let's say you have hyperplanes in 3 dimensions. Okay, do you see that the complexity of the whole arrangement would be n to the power 3? Well, what's a vertex in this 3-dimensional arrangement? It's an intersection of, one plane, a second plane gives a line, a third plane gives a vertex. So a vertex is the intersection of 3 of these planes. And actually, when the planes are in general position, then any 3 planes will give you a vertex. Okay, so n to the power 3 for the number of vertices, and you can also prove that it's the same for the number of edges and faces. So if you look at envelopes, then in general you lose one factor of n. So from n to the d you go to n to the d minus 1. For planes you actually lose much more. Okay, so think about the upper envelope of planes in 3 dimensions. What's the complexity? So I have but now these are planes, this is simply a convex polytope defined with n facets, and we know that in 3D that has linear complexity. Right? If you look at that convex polytope, if you look at it from above, you basically see a planar graph where every plane gives at most one face in the graph, and it's a planar graph, so by Euler's formula the complexity is linear. So for planes in R3 you get n to the power 1, and in general you get n to the power d over 2 rounded down. So can you, if instead of planes you have surfaces, like let's say very somewhat simple surfaces that look a little bit like this, or maybe like this, can you come up with an example where the upper envelope has complexity n squared in 3D? Okay, so for planes that's not possible because you get this polytope and it has linear complexity. For surfaces, well, think about, okay, so this is, imagine this is one surface, so here goes my surface. So it looks a little bit like, oops. So this is one surface, okay. Now take another one. So this is the intersection of these two surfaces. So it's a little bit hard to draw. Yeah, so I can take a number of surfaces like this. And then if you look at this from above, it's going to look at something like this. Right, so these are the intersections between two such surfaces. And now I can do the same thing, but rotate, and actually cut everything like this. So here I also do something. Maybe a little bit difficult to imagine, but so the point is that this bound is more or less tight, maybe except for the plus epsilon, but otherwise you can really get this, but not with hyperplanes. Okay, if instead of fully defined functions or unbounded curves, I have curves that can also have endpoints, right? Then we saw that the bound was lambda n plus 2, sorry, s plus 2. For segments can intersect only once, so s equals 1, so I get lambda 3, and lambda 3 was this n alpha n. Okay, so that's a bound you see a lot in papers, and that has to do with this thing. And again, the results extend to higher dimensions. Here, actually, even when you have linear surface patches, so let's say triangles in 3 dimensions, then the bound triangles in 3 dimensions, you still get roughly n squared. So for planes, it was like linear, but for triangles, you can get roughly n squared with this alpha. Okay, single cell. So this is actually a very nice proof, I think. So let's say we have a number of curves. Okay, each pair of curves intersects at most s times, and I look at one cell, one face. So this here, for instance, and I wonder what is the complexity of this face. Okay, so what I'm going to do again, the basic idea is to somehow use this Dev-Bode-Schinsel sequence machinery, but it's going to be a little bit more involved. So we'll see. We'll try to do that. So the first thing I'm going to say is that, well, if you look at a single face, a single cell, then the boundary may have lots of different components, right? You have maybe the outer boundary of the cell, but there are all these holes inside. And I'm going to do those separately. Right? And note that any segment can be part of only one of these components, because if a segment would be in two components, well, that would be one component. Okay, so I'm going to look at the different components of the boundary, but for now I'm only going to look at one component and then simply say, well, if I can prove something for this component, for the outer one, then maybe here for the outer face I can prove the same thing, and here I can also prove the same thing, and then simply add all these things. And because a segment or a curve appears in only one of them, that's good. So I essentially, let's say, even if I have many components, say component, let's say k components. Was there somebody who wanted to come in? Okay. So let's say I have k components. Then if I can prove a bound of, let's say, f of n for a component, then actually what it means that, for the first component maybe I have fn1, where n1 is the number of curves contributing to that component, plus fn2 plus f and k, where the sum of these ni's is at most n. And actually this is always going to be at most n. And that's because these functions are at least linear. Okay, so the message is, forget about this other component and let's just look at one of the components, and doesn't really matter that much, look at the outer boundary of this face. Okay? So now for simplicity I'm using n as the number of curves that contribute to this component. Okay, so what I want to do is something like, here I have curve 1, here I have 2, maybe here also 2, here I have 1 again, here I have 3, and write this sequence and then argue that it's a Davenport-Schinzel sequence. Okay, but there are a number of things that make that you cannot simply do this. You have to apply a number of tricks. So the first thing is that for each curve, I actually going to, you can imagine splitting it into two curves, doubling the curve, so that for each curve, the single cell is always on the same side, right? Because let's say I've doubled this curve. Well, on this side, I have this thin region in between this one and this one, which is not going to be part of my cell. So for each curve, now it could be that at some point this red portion also appears here. So for instance, if you look at this curve, okay, I've doubled it, and you see that both the red appears, but also here the blue appears, and here the blue appears. But for each of my new curves, you always have the cell on the same side. And on the other side, there's this thin region. Okay, so this is the first thing I do. So that means maybe instead of having, if I write my Davenport-Schinzel sequence, instead of having n symbols, I now have two n symbols. Because this one and this one get a different symbol. Okay, so the first thing that we will need to prove is what is called the consistency lemma. And that's the following. So look at one curve. Let's say this red one, gamma. Okay? Look at all the pieces of the curve that are an edge of the face that you're looking at. Okay, so the green thing is the face. So here I'm on the boundary, and then here and then here, and look at them in order. Okay, so first this one, then this one, then this one. Now what you can also do is look at the same edges, but now not ordered along the curve, but ordered along the boundary of the face. Okay, so now if I go here, instead of following the curve and looking at all these pieces, I'm going to follow the boundary of my cell. Okay? And as you can see in this picture, that actually has to be the same. So here this cannot happen, right? It cannot be that I first have this, and then if I, let's say this is the first one along the curve, that if I go to the next one along the boundary of the face, that I suddenly get to the third one along the curve. Well, why not? If there's something in here, I mean, this is the boundary of the face, so this somehow can never connect to here. Right? And know that for this, I actually need this splitting of this curve, because if this would be on the other side, then it could be connected to here. Right, so indeed, if I only look at this part, let's say the bottom part of the curve, then the ordering along the curve is the same as the ordering along the cell boundary. So this is something that we will need and that we need to remember. Okay, so now let me define the sequence. So I'm simply going to write down the symbols, but there's one other thing, small technical thing that we need to do, because a Devboj-Schinzel sequence is a linear sequence, right? It starts somewhere and it ends. The boundary of my cell is circular. So that's different. So I have to start somewhere and then turn it into a linear sequence. And there's a little detail in the proof that makes that you have to do one little change, and that's the following. Suppose I start here, my sequence. Okay, it doesn't really matter where you start. Let's start here. Now I'm going to write, gamma 1, gamma 2, here I have a gamma 3, and so on. Here I have another gamma 3. Here I have maybe my gamma 3 on the opposite side, so that's a different symbol, and so on. And what you see is that, or what we have to do is, if you look at this gamma 2, okay, there's actually a portion before the starting point where, let's put it differently. If I look at the order along gamma 2, then if I start here, the first thing I encounter is not the first one here. Right, so basically this consistency lemma that I had, that the ordering is the same along the boundary and along the curve, that somehow messed up because I take the circular order and I open it up somewhere. And therefore, I'm going to write different symbols for this one and for this one. Okay, so if I look at a curve like this gamma 2, look at all the pieces that you get along the curve, then the ones that come before the starting point get a different symbol from the ones that come after the starting point. Okay, so how many symbols do I have in my sequence? No, I mean, I don't mean how long the sequence is, but simply how many different symbols do I use. I started with n curves, so I was going to use maybe n symbols, but now how many do I end up with? 4n, right? Because first I doubled every curve, So I get 2 n symbols. But then for each curve, maybe I also use 2 symbols, one symbol before the starting point and the other symbol after the starting point. So in total I have 4 n symbols. And now I claim that what you get if you do it like this is a Debwart-Chinsel sequence. So let's try to prove that. So
no, continue of gamma 2 it will be gamma, for example, 3 or 4. The continue of gamma 2 will be in the face.
here?
No, after
Here?
Yes. So it will be another symbol. It will have another symbol.
No, this is also going to be gamma 2. Right? Because it's the same curve plus it's if I look at it along the curve, it also comes after this starting one. So all the ones here that come after this one, they're all gamma 2. And the ones that come before, well, in this case only one, have my gamma 2 star. Okay? Okay. So I claim that this is a Debwart-Chinsel sequence of order S plus 4. So let's see how that works. This is actually, I think, a very nice argument. So I claim that there cannot be, well, alternating subsequence of length S plus 4. So somehow, of course, what I have to do is I have to say, well, if you have such an alternating subsequence, you get lots of intersections, and 2 curves intersect at most S times. Okay? So that's roughly what I want to argue. So let's look at a subsequence ij. Okay? So here I'm going to, the subsequence is along the boundary of my face. So here maybe I have curve I. Now I travel along the boundary of my face. I get J. Go further along the boundary of the face. So here other things happen, I don't know. I get I again. Maybe I get another I don't know. But after this I travel, and I get J. Okay, and then I can go, maybe lots of things happen here, but eventually you get back here, because the face has a circular boundary. Okay, so in this picture, you see that there's an intersection here between these 2 curves. Okay, and if I have, so let's say I have I, J, I, J, I, J, and so on. Okay, so here I'm hoping to show that you always have an intersection. Okay, then maybe here I also have an intersection. Here I also have an intersection. So, well, let's say that we have an intersection here. Then I want to argue that the intersection you get for this one cannot be the same as the one you get here. And this is because here the intersection is between, well, from this, it's, well, this part of the curve with this one, right? And that's a different intersection from this one with this part of the curve. Okay, so that means that if I can show that I have this intersection here, okay, then for each 4 consecutive ones, I get a different intersection. And that means that, you cannot have this alternating subsequence of that length. So now the main question is, why must there be an intersection here? Well, of course, you can make some kind of drawing and then stare at it for some time and then hope that there are no different cases somehow, but that's not really a proof. So we want to prove in a little bit more convincing way that there must be an intersection. And actually an intersection between this curve going from the first occurrence to the second one, so this one, and these ones. Okay. So if you want to argue that there's an intersection somewhere in some planar thing, what is the tool that you maybe have? Yeah, so we will do it by contradiction, or, so let me ask differently. So essentially you have some kind of planar graph with all these curves. So when do you know that a planar graph has an intersection? Then let's say a graph in the plane, right? So it's not planar because then by definition it doesn't have intersection. But if you just draw, some nodes and curves between them, when do you have an intersection? Well, when you have a K5 or a K33. So the trick, or what you usually try to do in these cases, is to somehow come up with some kind of K5 or K33 somewhere. So that's what we're going to do. So I'm going to define a graph here, namely the following graph. So you see 5 nodes. Okay, so for this piece of the curve, I'm making a node. For this, I'm making a node. For this, I'm making a node. Here, I'm making a node. I have 4 nodes, and I put a 5th one somewhere. Okay, so these are my 5 nodes. And I'm going to construct connections between them. Okay, so this node is inside the face, so I can just take a path that stays in the interior of the face to each of the other ones. Right, and that's possible because, this is a single face, so by definition you can connect everything in the face. Otherwise it would be 2 faces. Okay, so the other edges I'm going to look at is, from here to here. I went from here to here along the boundary of my face. So this is going to be another edge between this node and this node. Okay? I have an edge between this node and this node. I have an edge or a curve connecting from here to here. And actually also from here to here. Okay? And note that all the edges I've been talking about so far, they don't intersect each other. Right? All the white edges, I can just make sure like this that they don't intersect each other. The white edges stay completely in the interior of the face, so they're not going to intersect these boundary things that I'm using. And these boundary curves, they're simply different parts of the boundary, so they don't intersect each other either. So now I have, an edge from this node to all the other nodes. From this node, I have an edge to, to this node, to that node, to that node, and so on. So, if I now the other edges I'm going to use are, I'm going to connect, so this already had a connection to this guy, a connection to this guy, a connection all around to this one. So I only need a connection to this one. So I'm simply going to, these were both parts of the same curve, so I'm going to follow the curve. Okay. Similarly, for this one, I have all the connection I need except to this guy, and I'm going to follow the other curve. Okay. Well, this one already had 4 connections, and now this one, well, it has this one and it has the other 3. So now I have a K5, right? 5 nodes. Between every pair of nodes, I've drawn an edge. I've argued that there can be no intersections except maybe between these two. But it's a K5, so there must be an intersection. So these two things must intersect. Okay, so no matter how you draw it, it doesn't matter, you must have an intersection. Okay, so indeed, so this was the curve from here to here. From here to here. This is the curve from here to here, and they must intersect. Okay, so this shows that indeed the complexity is, well, you have an order, the Poisson sequence of order s plus 2, so the complexity of the phase is lambda s plus 2. Okay? So it's the same as the upper envelope. Right, the complexity. Upper envelope was also lambda s plus 2. If you have curves with endpoints, so here is also lambda s plus 2. Again, for segments s equals 1, so you get n alpha n. Okay. Next substructure. This is going to be very short. Just going to test a little bit how smart you are. So let's see. So the zone is defined as all the cells that intersect, well, if you have the zone of a line, all the cells that intersect that line. Okay? And now, if you look, for instance, at the zone of a line in an arrangement of lines, okay, how many cells does it intersect? N, right, or n plus 1 or something like this. Right, it intersects all the other lines and you always go to another cell. So you could say, well, I know that the complexity of one cell in an arrangement of lines is linear. I intersect n of them, so maybe in total, if you sum up all the complexities, it can be n squared. But perhaps a number of you who took computational geometry course have seen that actually the total complexity of all the cells is only linear. Right? So apparently some cells can have linear complexity, but if you look at all the cells along a line, then actually most of them are very small, and there can be only a few that maybe have high complexity. Okay, so this is O of n. Okay, so this is the small question. So now suppose I give you segments. Okay, so let's look at the number of segments. I don't know. And now I look at a line or a... Okay. And I look at the complexity of all the cells that intersect this line. So it's going to be, this one here, this is one of them. Here, this is another one. Another one. Also the unbounded phase, so actually here almost everything counts. So any idea how much the complexity can be? Well, so of course it could be n alpha n, because, well, I didn't say that we only prove the upper bound, but there are actually cells that have complexity n alpha n. So even a single one of those could be n alpha n. So actually there's a very simple argument that shows that even the complexity of all the ones in total sums up to no more than n alpha n, order n alpha n. And it's just, well, one tiny trick and then it becomes trivial. So can you somehow transform this arrangement, change it a little bit, such that suddenly all the cells intersected by this line become one single cell? Yeah, you could shorten that the segments, but then that's going to be hard to argue. So, for instance, look at these two cells. They're different. Right? I want to make it into the same cell, so I'm going to make a little cut here. Right? So in the picture, I take, along the line, I'm going to make little cuts. Now everything is connected together, right? Because all the cells, well, are connected through these little openings. What happened to the number of segments? At most twice, right? Every segment is maybe cut into two, so you have at most 2n segments. So you get, well, O of 2n alpha 2n, so still O of n alpha n. So very nice trick. Okay. Okay, so the final thing that I want to show is something about levels, k levels, because here also the proof is, I think, really very nice, and a proof that applies. The technique has been used in many, many places, so it's good to know this technique. So what's the level? I already explained a little bit before. Let's say we're now going to look only, for simplicity, at arrangement of lines. Okay? So if you're on a line, count how many other lines are below this point. Okay? And then if those are k lines, then you're at the k level. Okay, so here everything has one line below it. So this is the one level. Did I add another one? No, maybe not in this picture. So this here would be the 0 level. This thing here would be the 2 level, and so on. Okay? So that's the k level. The at most k level is simply everything up to level k. So level 0, 1, 2, 3, up to k. So what's the complexity of the 0 level? N, right? It's the lower, this is called the lower envelope. It's the bottom side. And that's, in this case, is the convex convex region. So I want to talk about this, well, especially the at most k level. The k level, if you want to become famous, then you should prove the exact bound on the size of the k level. The best bound is n times k to the 1/3. And nobody knows what the correct bound is. So if you can prove n log k or I don't know, then, or improve anything here, that will be wonderful. It's probably very hard because lots of people, lots of famous people looked at it. But it's not necessarily very hard because before this bound, there were already many, many people looking at it, and the best bound was n times k, or maybe nk over log k at some point, and then somebody proved this n times k to the 1/3, and that's turned out to be a very simple proof. So it might be easy, it's probably very hard, but maybe if you just have one very smart idea, who knows. But I want to look at this at most k level, and there we know what the exact bounds are. So the exact bound is that the at most k level has complexity n times k, or actually I should write n times k plus 1, because otherwise for k equals 0, well, it doesn't work. But let me just write n times k. Right, so for k equals n, or well, n minus 2 maybe, then you have the entire arrangement, right? Because you take the 0 level 1, 2, 3 up to the n minus 2 level, and that's simply everything. So indeed it's n squared. And now we're going to prove that this behaves like this. And as I said, the proof is very nice, very easy also, and it's a very useful proof technique. So for instance, if you want to prove something about the k level in an arrangement of segments, you can immediately apply the same technique. Okay, so what's the technique? So this is in a paper from Clarkson and Shor, and it's usually called the Clarkson-Shor technique. So you take a random sample of your lines, okay, where you pick every line with probability 1 over k. Okay. Now let me define f at most k of L as the complexity of what I want to bound. Okay, so I want to show that this is actually equal to order n times k. So now look in the at the sample R. Okay, so I have all the lines. I take some of the lines, and now I'm going to look at the 0 level. Okay, so here I have lots of lines. I don't know, well, many. I'm going to take a sample. So for instance, I'm going to take this line and maybe this line. So this is my R. And I'm going to look at the 0 level of this sample. Okay? So we know that the 0 level, if I have a set R, well, the complexity is at most a number of lines in R. Okay, so the expected number of vertices of the 0 level is at most the expected number of lines in my sample. Well, if I pick every line with probability 1 over k, I expect to have n over k lines. Okay, so this is the first thing. Now, I want to have a second bound on the complexity, the expected complexity of the 0 level. But now, in terms of this thing, and then by combining these two things, we will get what we want. Okay, so I'm going to bound this same quantity, but now in a different way, namely as a function of this thing. So let's see how this works. So look at a vertex which is in my at most k level. Okay, so what does it mean? I have a vertex and the number of lines below it is at most k. Okay, if it would be exactly at the k level, it would be exactly k, but I'm looking at the at most k level. Okay, so here I have L lines at most k. So what's the probability that this vertex here now becomes a vertex of my 0 level? Okay, so what has to happen? I must have picked this line in my sample. I must have picked this line in my sample. But I'm not allowed to pick any line below it in my sample, because then it's not on the 0 level. Okay, so the probability is simply, well, each of these lines is picked with probability 1 over k. So I have to have both, so that's 1 over k squared. And all the other ones I'm not allowed to pick, and that happens with probability 1 minus 1 over k. Okay, so this probability is simply 1 over k squared times 1 minus 1 over k to the power L. Right, since this is smaller than 1, so this is at least, well, I replace L by k. Since this becomes bigger and this is, I'm only making it smaller, so this is bigger than this. And, well, this is bounded by 1 over e. Okay, so this is a constant. That's something you have to know. So this probability is 1 over k squared times this constant here. So what's the expected number of vertices on the 0 level? Well, I get, let's see, yeah. So basically the expected number of vertices is, well, I guess equal to the sum over all vertices of the probability that V is on 0 level. Okay? Well, this is of course at least the sum V is at most k level in the full thing, right? Instead of summing over all vertices, I just look at some of them. So this probability is definitely bigger than this. And here, this quantity is simply, well, at most, or at least, the number of things there times this probability. Okay, so the expected number of vertices at the 0 level example is at least the number of vertices in the original set that were at the at most k level times this probability. And now we're done because, well, we already knew that this was at most the complexity of R, which is expected to be n times k. We also know that it's at least this. Put it together, and you'll see that this must be smaller than, well, you know, put this to the other side, you get n over k divided by 1 over k squared, so n times k. And this is a constant. Okay? So the nice thing is to apply this technique. The only thing you need is essentially this. Right? As soon as you know that the expected, so you always relate somehow things to the complexity of the 0 level. So if I now want to do this for segments, well, instead of nk, I have to write nk alpha nk, right? Because the 0 level, the lower envelope of segments was order n alpha n instead of order n, so I get this extra alpha. This remains exactly the same. So you get this times some alpha. And there's lots of different other scenarios where you can use this. So you need a bound on some kind of 0 level, and you need to bound the probability that something appears there. And that's it. Okay. To summarize, so we looked at lots of different things in arrangements. Full arrangement, well, that's quite easy if you look at the complexity. Upper envelopes, in one dimension, it's essentially linear. You get this bound relating to the Davenport-Schinsel sequence. You also get bounds in higher dimensions. And if you want to construct these things, so if you want an algorithm to compute the upper envelope, or you want an algorithm to compute the full arrangement, then for most of the things, you can do it in roughly the same time. Maybe there's an extra log factor or something like this. Same thing for single cells. We've seen these bounds, and for the at most k levels. And again, most of these can compute it in roughly the same time as the complexity. So that's it for today. Are there any questions? No?
So,
Oh.
maybe a similar proof for the complexity of the single cell that is similar to upper envelope of bounded curves. We can see the boundary of the single cell as the upper envelope of bounded curves. So maybe there may be a simpler proof for that theorem.
Possibly, but I expect not. I mean, essentially, this proof is already trying to say, okay, take the proof for upper envelopes, which is this Davenport-Schinsel sequence, and now apply it here. But because, if you have a cell, then it's not a linear sequence, but circular. And I mean, essentially, I think all these things you need to somehow adapt the proof. And then I think this is what you end up with. But it might be that indeed you can do it a little bit simpler. But I don't know. It would be nice if you could simplify it. Okay, so that's it. Thank you.